Ed Penner, seconds.
Thank you. Hey, good morning, Ed. All right.
Good morning, morning.
Okay. Waiting for the little pause here. If there's no objections, then we'll go ahead. I'm hearing none. So, Steve, now we're back to the presentations. I think we're going to do that first. And I certainly want to move my comments further down the meeting, but we'll see how this all plays out. But let's try the presentation there first. You have
Right.
in
So
those
can I,
back.
if I may, Mr. Chairman, I'd just like to speak to this before they start off.
Yes. Yes.
So, I have the luxury of being able to get out and see many activities that are happening out in the field. And one of the things that truly recognizing is the need of some of the municipalities when it comes to meeting the releasing targets for their lagoons. And I know many municipalities are faced with considerations of having to do change up, maybe increasing the lagoon sizes. Like there's many obstacles that are before them in order to meet the new legislation requirements. Um, Dealing with an advantage and being able to listen to their presentation as they wrote in the Arm of Taché was quite engaging for me, and it was amazing work for what they were doing. And I really want to make sure that we're able to get that out there and share that with many of the municipalities within the basin. This may be an alternative for you if you're trying to meet your targets and trying to increase the capacity of your lagoons. So I wanted to bring them in and allow them the opportunity to do that presentation. Gavin, I don't know if you're going to speak first or if Armand, you are, but please take it away.
Yeah, I'll start. And Steve, if Armand is able to share his screen, he'll manage the PowerPoint presentation from his side.
Sounds
Um,
great.
yeah, so thanks, Steve, for the opportunity, and thanks to everyone for joining us. It's a privilege for me to be able to do the presentation. Thanks, Steve, for the invitation. As Steve mentioned, as we've been going since 2016, there's been legislation to regulate phosphorus in wastewater discharge. And so it's been on our mind for a long time, and we've been working on the research for this project for about 2.5 years now. And so we're going to give some of our findings at the end. We did a large study last year with the Lake Winnipeg Basin Program through Environment and Climate Change Canada. And so Armand is going to present that study and some of those findings, which are really interesting. But as Steve said, our goal from the beginning was a couple of things: to make sure not just that we precipitated phosphorus in municipal lagoons, because the phosphorus is a major contributor to algae blooms in Lake Winnipeg, but also that we approached it with a circular economy approach. So making sure that not only that we precipitate the phosphorus, but we capture it and then reuse it. So part of the technology that is being developed behind the scenes is capturing the phosphorus and composting it and returning it to the municipality so that they can have a beneficial reuse of that phosphorus. So that was key in the beginning. The other key is that there are technologies out there currently that do it. So we set out initially to make sure that we could do it in a more affordable way and make it more affordable for municipalities. So that is a background. I just want to, Armand, if you go to the second slide, if you can put it in presenter mode, maybe.
Oh,
There's,
uh,
I,
is it? Are you seeing the presentation now?
I'm just seeing the screen with all the slides on, not the full presentation.
Oh, uh, but you should be able to see it because it's in the presentation. It's in the presenter mode
I'd
actually
just
right
be
now.
sharing the wrong screen. It doesn't matter. I'll carry on presenting. That's fine,
No,
Armand.
no,
So
no,
just
I
the
mean,
team that, yeah,
yeah, I will try to
yeah,
definitely.
that's fine. So
Let
the
me
team that's
see.
presenting is myself, Dr. Armand Vahedi, who's just getting the presentation going. He's my business partner, and he was overseeing the research. And then Mang Mang Tian, she's one of our other staff, is she did a lot of the testing, and she ran our lab last year. So that was how the project went. Armand's going to give a brief overview, but as we do that, currently we're also working, and I've asked them to sign in. Ali is signed in, and he's a master's student at the University of Manitoba, working with us on some research projects, and he does have a PhD previously as well. and Aidan, who's a PhD student at the University of Manitoba. They are currently working with us on ongoing research. But Armand, do you want to
Yes.
take
So
it
do
away
you
and
see?
explain the Lake Winnipeg
Yes.
Basin? Yes, we see
Yes.
it.
You see it now. Good. So,
Yes.
Gavin, thanks for the introduction, and good morning to everyone. Thanks for having us presenting the findings of our research to you guys. Uh, just to give you a little bit of background again, these are most of you know already that in Manitoba we have a large number of municipal and First Nation community lagoons that either are facultative or aerated, approximately 350 of them. As of January 2016, as we know, there's a regulation of the total phosphorus discharge for lagoons that should be not more than 1 milligram per liter. And for newer expanding plants which discharge less than 820 kilogram per year, they have to also meet. They have to meet the 1 milligram per liter limitation, which could be challenging for small municipalities because of the price point and cost of treatment. Uh, we looked at different phosphorus removal methods that are currently happening in uh, basically prairies, I would say. Phosphorus removal methods, we could have biological phosphorus removal methods, which means you just let the lagoon do it naturally. Uh, it's been proven almost that it's not sufficient to meet the 1 milligram per liter limit, especially in cold climate conditions. Uh, in situ chemical coagulation, it's another method. Basically, what do we mean by this is just applying alum or ferric chloride directly to the lagoons. That is the most common method in Manitoba, which you pour the chemicals directly to lagoons. Usually, they do it by a boat, and it is inefficient when it comes to mixing. It results in the precipitation of phosphate particles in the form of sludge, which could reduce the lifespan of lagoons. And those who have gone through that route, they know that the desludging or dewatering of lagoon and dredging is a very expensive process. There's also a chance when you do this kind of chemical coagulation, there's a chance that phosphorus is released back to the water and could be released back to the streams. We also looked at ex situ chemical coagulation. Basically, we mean that you treat the wastewater in a separate plant. You pump it from the lagoon and treat it in a separate plant. There are a couple of examples of these in the province of Manitoba. It needs a particle separation system. Existing systems that I just mentioned, they're either inefficient or extremely expensive. So we'll get back to that. We also looked at engineered wetlands, which have been established in a few municipalities. It's a form of biological treatment again. It is low maintenance, but requires large footprint and usually is expensive. So, what is the challenge of monitoring? We specifically looked at monitoring because we specifically wanted to know what is the relation between these phosphorus methods and the monitoring that we have. So, the challenge of monitoring for the municipal lagoons, the current phosphorus monitoring approach in Manitoba is to measure phosphorus levels at the lagoons prior to discharge, and as soon as you meet the 1 milligram per liter phosphorus, the discharge starts. In lagoons with in situ coagulation, those that actually apply alum or ferric chloride directly to the lagoons by boat, the process results in the precipitation of phosphorus in form of sludge at the bottom of lagoon. And when the discharge starts, this settled sludge that is closer to the bottom can be disturbed and suspended back to the water. And slow degradation results in release of phosphorus to the streams, and also another issue is because when you start the discharge, you also always take the samples closer to the surface. However, the discharge pipes are actually closer to the bottom of the lagoon and to the sludge. So as a result, when you actually start discharging, lots of particles could be disturbed and go in and enter the water, and your results may not be exactly as what you've seen. You could be much higher and could be even exceeding 1 milligram per liter. So that was our hypothesis. We wanted to prove this. And that's why we worked with Lake Winnipeg Basin Program, and we started a project when we looked at 14 lagoons close to the main stem of Red River in the Manitoba portion, in the Manitoba section of the Red River. I know that some of the municipal officials are here, so your lagoons could be actually included in this study. However, we do not disclose any names or any exact location for the lagoons. We planned 6 to 7 duplicate samples during the discharge period. For 2 of these 14 lagoons, the short discharge period and harsh weather conditions prevented us for collecting all samples, so we had fewer samples than 6 to 7. And we analyzed the samples for total phosphorus. We analyzed the trend of total phosphorus variation for each lagoon, and we wanted to see the result. So here is the geographical location of the lagoons that we picked and we tested. So the characteristics of these lagoons, again, this table might be overwhelming a little bit, but we color coded these lagoons. The orangish ones are the ones that actually use in situ chemical coagulation, either by ferric or alum. Basically, they apply alum or ferric directly to the lagoons. A total of 7 lagoons were in that category. And as you see, there are different sizes. They serve different populations. So that kind of gives us a good sort of population of lagoons to start with. We also have the ones that are actually color coded light blue. They have no treatment. They only rely on biological treatment. The one with pink color is the one that uses a plant and does the ex situ chemical coagulation, and the green one is the wetland. And then we looked at the trends of total phosphorus in the discharge during the discharge period. So at first, we just looked at the in situ coagulation lagoons, the ones that actually apply alum or ferric directly to lagoons. As you see, number 4 and number 5, for example, in this slide, they show increasing trend of phosphorus, total phosphorus, throughout the discharge. And as you see, the discharge period for the number 4 is only 10 days. For number 5 is only 9 days. So for 10 days or 9 days, you see an increasing trend of total phosphorus, especially for number 4. It begins at 0.3 and goes all the way to 1.6 at some point, and at some point is at the end is around 1.2, 1.4, and definitely above 1 milligram per liter of the regulations. For number 5, the same trend is evident. As you see, it was below 1 at the beginning of discharge, but increasingly exceeded the 1 milligram per liter and showed an increasing trend. For 2 other lagoons with the same type of phosphorus removal strategy, number 6 and number 9, again, even though they didn't quite go above 1 milligram per liter, the increasing trend is very visible. We also looked at number 10 and number 12, another 2 lagoons with the same phosphorus removal system. Again, increasing trend. This number 12, as you see, very obviously goes above 1 milligram per liter. And number 13, again, increasing. And another observation that we made was, as you see, for example, for this lagoon, the total phosphorus is going to below 0.2 milligram per liter at the beginning of discharge, which is something that, as an engineer, I would say is unnecessary. It shows that you have used too much chemicals, and too much chemicals, it means too much sludge at the bottom of your lagoon and decreasing the lifespan of your lagoon significantly. Same happened for number 10 and as well as number 9, which number 6 probably was the best one here because it started from 0.4 and went all the way to 0.8, still stayed under 1 and wasn't too inefficient. But number 9 also used too much chemicals for sure. Because again, if you want to meet the regulations, you don't need to go to 0.1 or 0.2 milligram per liters. So what was our observations? We showed that there was an increasing trend of total phosphorus for all monitored lagoons. which used the in situ coagulation. 3 of them exceeded 1 milligram per liter at some point, and the phosphorus removal by this method seems to be also inefficient because we saw the values as low as 0.2 and even 0.15 in some of those lagoons, which is not necessary. Does this prove our hypothesis? Yes, because it is not easy to explain the reason of the increasing trend in total phosphorus in any other way. Remember, this whole discharge period was in a matter of like 7, 8, 10 days. So within 10 days, you don't really have any other explanation other than having disturbed sludge or sedimentation going back to the discharge. Because the way that we test the total phosphorus and the way that all certified labs test total phosphorus is they digest the samples. Basically, all the particles that go into water, they will show in your total phosphorus results. And now let's go look at the only ex situ coagulation lagoon that we actually have in this study that shows pretty consistent and even decreasing phosphorus trend. The sludge doesn't enter the secondary lagoon in this case and consistently meets the total phosphorus limit of 1 milligram per liter, which further proves our hypothesis because this one shows that we don't really have any increase. So it's only the only one that wasn't really using in situ and using ex situ coagulation and actually showed a good trend. By the way, this year we are continuing the research with a larger number of lagoons, and hopefully we will have more data on all these categories of lagoons by the end of 2022. Lagoons with engineered wetlands. Again, we only had one lagoon in our studied lagoons, which used engineered wetland. As you see, the trend was increasing and showed even above 1 milligram per liter at some point. At the beginning was very low, was really clean. The temperature may have affected the process. We know, as a matter of fact, that engineered wetlands are actually very effective in removing phosphorus. However, as you see, the discharge period was only 35 days. After we consulted with professionals who had more experience in engineered wetlands, we figured that most likely the longer hydraulic retention time would be required. In fact, that specific wetland that we tested was designed to have somewhere between 45 to 60 days of discharge, not 35 days. So definitely it was a really short discharge, and that's why it didn't really show effective removal. The increasing trend, again, could be due to the sediment coming from the bottom of the lagoon into the wetland and showing up in the discharge. With longer hydraulic retention, you could also avoid that slightly. I mean, you could still see some trend of increasing because, as you will see, with lagoons that even have no phosphorus removal, you could see that increasing trend just because you have particulate phosphorus from sediments entering your discharge. So now let's look at the lagoons that have no phosphorus removal in our study. This number 1 and 2. As you see, they're not meeting 1 milligram per liter phosphorus removal limit. Number 1 is above 6 milligram per liter all the way, and they show also slight increase in the discharge throughout the discharge period. The first one was only 3 days discharge, and the second was only 7 days, and still showed some increase. And as well as number 7, which had 35 days of discharge period and showed an increasing trend from 2 to 4.5. Number 11 as well, only 5 days of discharge, pretty consistent level, but above 1 milligram per liter. And again, the last lagoon that's also showed increasing and also above 1 milligram per liter total phosphorus. So what was the conclusion from looking at the lagoons which had no phosphorus removal? Our conclusion was that natural biological treatment, at least for Manitoba, which has very short summer, doesn't lower total phosphorus to below 1 milligram per liter. The increasing trend is evident. It is most likely due to the mixture of the disturbed sludge at the bottom of lagoons, which usually contains particulate phosphorus. So that's another trend that we actually observed, and it looks like that mixture of sludge actually exists, and our hypothesis all along was pretty good. I would say it's correct. So why is it important to contain and recover phosphorus then? Uh, we want to we claim that this is actually very important. It's important to actually take the phosphorus out of the system, not to just pour alum and ferric into the lagoon and let it settle. Because the sludge is disturbed during the discharge period, the phosphorus can be released back into the effluent, and in situ coagulation therefore may not be a good idea, and it is important to contain and recover phosphorus. Also, we know that phosphorus is a valuable commodity, and phosphate rocks are limited resources. Tons of phosphorus is wasted in wastewater, and therefore it is also another reason that we think it is important to contain and recover phosphorus. How to recover phosphorus? We call it an innovative approach. We knew we wanted to recover phosphorus because this is something that we knew we wanted to do. We wanted to make sure we take the phosphorus out of the system, not just let it settle at the lagoons. We also knew that chemical coagulation most likely will remain the most cost-effective phosphorus removal methods for lagoons. We did that by doing research on myself and working and Gavin and working with University of Manitoba. We started from that point. We researched the bioavailability of phosphorus in sludge. We started working with Dr. Yuan at the University of Manitoba, and we conducted a large-scale sludge dewatering and composting test in collaboration with the city of Selkirk. Preliminary data were pretty promising. Therefore, we started actually building a system that we could capture and recover phosphorus. I give it to Gavin to talk about that from this point.
Thanks, Armand. So, as we mentioned in the beginning, the key, I'm just going to describe some of the processes worked through and not so much the products we've developed. The process is very key. And as Armand mentioned, the key has been a circular economy approach where we work on capturing the phosphorus. Two benefits surrounding that is, well, a couple of benefits. Phosphorus is a limited resource. So now and more so into the future, it'll become more and more critical to not waste it and capture it and reuse it. The other thing with capturing the phosphorus is there's a number of ways to do that, but the way we have developed does have a chemical application as well. So the two benefits of a process like this is that you do use less chemicals, firstly, and secondly, that the chemicals are not discharged into the environment. They are captured with the phosphorus and then go through a process. The final capturing part has to do with composting. So here's the process. Water is pumped from a lagoon, goes through a coagulation, flocculation process. What that is all about is some chemicals are added, like ferric and alum, that attach to the phosphorus and make them large enough to capture. So that's the key. That piece, the physics and the chemistry around that are a key to the process. It then goes into a particle separation tank. That is probably the biggest key to the entire process, where we will get clean effluent out one side and the phosphorus sludge comes out the other side. The sludge is then pumped into a dewatering bag that is able to drain. The clean water goes back to the lagoon from the dewatering system, and the dried sludge is then taken and composted. This is so we have there, it is fully recovered. We've been working with the university on this for a while, and it has been, it is a challenge because you are dealing with a complicated sludge. It's not your regular sludge that comes into the lagoon in your primary cell. When we're capturing sludge from the secondary cell, if you've seen lagoons, the secondary cells, especially towards the end of the season, are very clear, very clean. They've gone through the entire process and they're basically ready to discharge. So the water is clean, and all we're doing is taking the fine particles, the phosphorus, and any suspended solids out. So the characteristics of that sludge are different to regular wastewater sludge, and composting that, we have been successful. Our goal is to get it to a category 1 or class A biosolid, and that is requiring a bit more work, and hopefully by the end of the summer, that work with the university will be completed. This picture that Armand has put up reflects the pilot scale study. So that we conducted in the RM of Taché, the landmark lagoon. We had a full particle separation tank with all our chemical treatment, etc., and we managed to treat the lagoon on the left-hand side was 110,000 cubic meters. We managed to pump, separate, and capture the phosphorus, which is the phosphorus that we are currently using with the university. During the process, we ran tests every single day, multiple tests on multiple lagoons, and we monitored every moment of what you did. So there were hundreds of tests. We managed to capture and remove 85 to 97% of the total phosphorus, and we treated 110,000 cubic meters of wastewater during the summer of 2021. We are currently still at that lagoon. We had the winter to look at our data and run some new tests. So that was a key, and we continue to run tests on that. And also, there's been a couple of processes that have been developed right now, and together with the two other gentlemen we're working with from the university, Ali and Aiden, they've been working with us, and we've, in the last few weeks, the weather has been a challenge. Getting onto those lagoon cells with this consistent rain has been a challenge, but the processes that we've developed, the efficiency that for the phosphorus capture and removal is incredibly high and significantly higher than what is currently out there in Manitoba, and actually generally as we've done research with other engineering companies around North America. The technology that we've been developed there's keys to it. It has to be able to consistently reduce phosphorus to below 1 milligram per liter, and we've been aiming at below 0.5. At the same time, as we're capturing particles, it does reduce the TSS and the BOD in municipal lagoons by between 40 and 60%. So if we're capturing 98% of the phosphorus, we're also capturing half of the TSS and BOD. So if a lagoon does have suspended solids or BOD issues, it can support that as well as optimized use of chemicals. We're using 40% less chemicals than in the traditional approach, and they are not entering the environment. The phosphorus recovery, that was a key when we started. It's a unique piece. I know that the city of Winnipeg does run a compost program with their sludge that they capture. However, no one else is currently that we're aware of is composting phosphorus precipitated sludge. The characteristics are very different, and we've been successful at that. We're working on it to perfect the process to make sure that we can consistently get a category 1 biosolid out of that, and probably wasn't as easy as we expected, but fortunately working with the university, we've been able to work on that over winter, and now we're just waiting for some fresh sludge to come out of our system. The key to the system is to keep the costs down, is that it has to be a small footprint. You don't want to be adding cells. I know a lot of municipalities with some of them are well suited to expanding, whether you have more land or another cell. Some of them, a lot of municipalities would struggle to add another cell just because land is not easily available, and you have to have land right next to your lagoon. And so the systems that we've designed currently are small footprint and run within the current area of the lagoon, and are the key again, besides the phosphorus recovery, has to be cost effective. So the next slide there, Armand. Yeah, so this is just a small picture of some of the composting that's happened at the university. They have a lab there where we have had the sludge and taken wood chips and other organic material and are currently composting it, and that's been monitored on a daily basis. The ongoing work and the final design we're completing this year for the systems. Armand and I are working on that. We are working with Dr. Chu Yen Wan from the Civil Engineering Department at the university, and the two gentlemen that have joined us, Aiden and Ali, as well as Saba. Those are the three students that are working with us on different aspects of this technology, that just finalizing the design and construction of that. And we're also working with Dr. Sferi, who's part of the mechanical engineering department, as far as automation, look at automation of the entire system. For municipalities, the goal is to be able to push a button and have very little human intervention after that. So in summary, the natural biological treatment within a lagoon without any treatment doesn't reduce phosphorus. We saw those results very clearly below 1 milligram per liter. The ex situ coagulation is effective, and the current plants that are out there are really expensive. Currently, the research we've done is between $2.5 and $5 million. So that just gives you a ballpark for those municipal officials as to what's currently out there. Engineered wetlands are really effective, and depending on the situation, there's a cost attached to them as well as land acquisition costs. And I know some of the challenges municipalities have had with acquiring sufficient land close to the lagoon for that. And the majority of lagoons in Manitoba use the in situ or alum dosing, which is the reason it's been used is probably the simplest. The capital costs are very low. Usually the municipalities have a boat and just charge alum or ferric off the back of the boat, and it's the simplest. But it does, depending on the municipality, if you're using $100,000 of alum every year and it's costing you 40% more than it should, that is an excessive cost. And so there's a need for innovative and cost-effective solution in Manitoba. The next slide there, Arman. Yeah, and so that's basically the presentation. We want to give you an overview of the research done with Lake Winnipeg Basin, as well as some of the processes developed in the full capturing and reuse of the phosphorus. And I guess, Steve, we're open to questions if anyone has any questions for us.
Yes, we definitely are open to questions. I do have a couple of, if I may start it off, gentlemen. First of all, what was intriguing to me is the fact that, the costs and the space issues. I know for a fact that there are many smaller RMs that are facing the possibility of having to add an additional cell onto their system. They may not have the room, as you stated later, and they may not be able to afford the expansion or get the funding in order to do so. Do you have like a ratio? I know that, let's say a cost of building a lagoon can be another cell could be, a few $1,000,000. Do you have a ratio like the size of a certain size of a lagoon based on what your treatment would cost? I hope I'm getting that across properly.
Yeah, I guess. So every municipality is unique and the characteristics of the wastewater are unique. We generally work on a flow rate. So there's two ways for doing a system. And in Manitoba, there's if you want to do ex situ coagulation or full phosphorus capture, there's a seasonal way to do it where you would be pumping from a lagoon cell for the 5 months over summer. And so that's a more inexpensive way because you can build a system that's a one season system, but it will have a higher flow rate. If you want to build a 4-season system, it's obviously more expensive, but you can go pump for 12 months and you have a lower flow rate. So there's a trade-off. Generally speaking, for a system like this, it would be ranging for most lagoons in the province. Some of the larger ones might fall outside of this, but would be in the range of 700,000 to under 1.5 million, depending on the flow rate that you have.
And this is far cheaper than the existing systems that are out there actually.
Right, right. And that's what was intriguing to me as I sat down and I went through everything with you gentlemen. The results were amazing for the cost and far less than having to put another lagoon cell in or having to deal with all of that licensing and everything that goes along with that. Just so. Also, to my understanding, if somebody's utilizing alum, doesn't that material have to be hauled out to a Class 1 waste facility and um, handled properly?
So
Like when they're
generally speaking, what has happened in lagoons, if you're dredging a lagoon, it is usually the primary cell where the water comes in because that's where all the solids are. The alum is usually added in the secondary lagoon and starts filling up that lagoon. So a lot of the secondary lagoons haven't been dredged and the alum precipitated sludge is sitting in there down, and they usually don't have sludge in. So now over time, we've only started doing this from having alum treatments generally from 2016. That sludge is building up in your secondary lagoon, which you don't normally. But we work on the composting is to make sure that is then restored into a Class A biosolids. So right now, Steve, to answer your question directly, I'm not aware of lagoons that have been pumping that have dredged their primary cells with LMN, but that is definitely a consideration. I believe it would be possible, if it is tested correctly, there may be the option for landfilling it. However, the province does not generally, without an alteration to your license, does not allow landfilling of sludge. The wording in the legislation is that it needs to find a beneficial reuse, and they generally don't want to put in a landfill. And so the composting process is probably the best way to get it to a form where it can be land applied.
And that's exactly correct, Gavin. And that's what we are trying to. I mean, again, with university, we are trying to open this dialogue that this whole sludge could be reused, and it is not toxic at the concentrations that we have. It is safe, and it is not going to kill some population of plants, because that's also very important. And that's exactly what is being done at university with a couple of students working on this, with Dr. Chuyan leading the research over there, to try to see how we can use this reuse this sludge and kind of take that burden off landfills and off the municipalities.
Right. I just recall that when I was the mayor of St. Clements and we were dealing with the province up in Grand Marais. We do have a question for you in the chat. It's coming from Larry. He's referring to the cost. So that's 750,000, 1.5 million. Is that capital cost only? And what is the annual operating cost for what you would be supplying to a municipality?
Okay, so that, yes, that is a capital cost. So there would be an offset for the municipality on the annual operating cost. There is some labor. There would be a number of hours a week that would be required for monitoring the system, as in any other system. The main operating costs would be the electricity, the hydro for pumping a large volume of water. So that's probably the biggest expense. And a part of that, not all of it, would get offset by the reduction in chemical use, and that's what the current municipalities who have it. There's generally speaking, what happens with the alum is dosing a lagoon with a boat is the least effective way for having particle contact with all of the phosphorus. When you're putting it through a plant, you're getting a much more perfect particle contact, which is the key to the entire system. So if you reduce your alum, depends on the costs, and as I've been speaking to municipalities, be somewhere between $20,000 and $100,000 for your alum. If you're reducing that cost by 40%, then that's your saving, and that will be offset by the increased. Most of your operating would be electricity, and then probably 5 to 6 hours a week, an hour a day of monitoring.
And our goal is to, again, as mentioned in one of the slides, is to have everything. I mean, this is exactly what our system is, having everything in a sea can shipping container 40 feet. And again, that's one option that we only operate that in summer, and over winter you don't need to do anything. And that also reduces the capital cost significantly. That brings it down to like closer to 700,000.
I hope that answers your question, Larry.
Yes. Is there any other questions? I see my chairman is back on. I see his smart looking face sitting there, or I did.
You did, okay, yeah.
There you go. Is there any other questions for anybody for Gavin or Arman?
Just one quick question. One quick question, Gavin. Anything about heavy metals in that sludge?
So that is tested, and in our current test that we've done for the composting when the sludge comes out, all the metals that are monitored are way below regulation levels. So they will always be found in trace elements, but not of any concern.
Okay, so no issue for root crops or things like that?
No.
No, thank you.
If I may, Mr. Chairman, what I would encourage anybody, if you wanted to get further questions or perhaps a presentation, I'm sure these two fine gentlemen and their colleagues would be happy to do that in person at your municipality. Probably the information would come across a lot clearer in person versus on our virtual platform here today. So you could reach out directly to them, or if you need us to help you create that link, we'd be happy to do so. I think as we're going forward, the province is starting to be very open-minded to new technology like this organization is working on right now. And when you're giving consideration to the cost of expanding your lagoons or putting in other major treatments, I believe this is a great alternative. So I encourage you to reach out for further information.
Yeah.
Thank you, gentlemen. We appreciate it, Mr. Chairman.
Yes, thank you. Thank you. And thank you, Gavin. I think his topic is very timely. In our case, we're dealing with a couple of small lagoons, and I think we may have to talk to you at some point. So sounds very good, Gavin. Thank you.
Excellent. Thanks, everybody.
Okay. Steve, we were still waiting for something to happen at 11 o'clock, right? Is that correct?
Yes, from the province.